Okay, this lecture is in the form of a tutorial where we are going to make use of a knowledge of being able to write difference approximations for any derivatives, both central differences, one-sided differences, higher order derivatives, higher order accurate schemes. All that thing we will put to solve a Poisson equation on a rectangular geometry. It is very much similar to what we have done in the very first week of this particular course, but we are going to make it more spicy by looking at different boundary conditions that we would not have been able to incorporate at that time, because we did not know this finite difference approximations, one-sided difference approximations and so on. So, the mathematical problem that we are looking at is given by equation 16 here, dou square u by dou x square plus dou square u by dou y square equal to f within the domain between 0 and L in the x direction and between 0 and capital W in the y direction. So, this is a rectangular for example duct with a length of L and a width of W, and this u here. So, this equation is very similar to the equation that we had for the W velocity component, and f here was the minus 1 by mu times dou p by dou z, and the u that we have here was actually the W. So, in that sense this equation is very much similar to the equation that we had in our very first lecture for flow through a rectangular duct, but we are going to now do it with the knowledge of finite difference approximations and how many different ways we can do it. Okay. So, we consider in the first case the Dirichlet boundary conditions. Okay. So, by that we mean where the value of the variable is specified on the boundary. Okay. So, which was also what we had in the first example, where we imposed the no slip boundary condition. So, we said that W is equal to 0 on all boundaries, and here G is the boundary, G of xy describes the boundary, and okay, on all points of xy lying on the boundary the value of u is given by G. So, G can vary, it can vary or it can remain constant, it does not matter. So, for a given boundary point defined by xi yj, the value of G is given, is known. Okay. So, for this is a 2D problem. So, we make use of a 2D grid defining it like I in this direction, x in this direction and y in this direction, and we have I plus 1, I minus 1 and that kind of notation for grid lines in the x direction. Okay, grid lines perpendicular to the x direction. So, this is all I minus 1, this is all I plus 1 like this, and grid lines perpendicular to the y direction are denoted by the symbol by the index j here. So, you have j here and the immediate upward neighbor is j plus 1, immediate downward neighbor is j minus 1. For the I, immediate right neighbor is I plus 1 and immediate left neighbor is I minus 1. So, the intersection of this y line and j line will identify the node ij. So, this node here has a left neighbor which is given by I minus 1 j, a right neighbor which is given by I plus 1 j, a bottom neighbor which is given by I and j minus 1, and a top neighbor given by I and j plus 1. Okay. So, with this kind of notation we can go back to the two derivatives that are appearing in this, and we can write a central difference approximation for dou square by dou x square at the grid node ij. This is a second derivative with respect to x here. So, we can write the corresponding expression as u I plus 1 j minus 2 u I j plus u I minus 1 j divided by delta x square, and this is second order accurate in delta x square in x. So, this is an approximation for dou square u by dou x square at the same j. So, j remains the same here, and when you look at this approximation, this is bringing in the value of u at the center at the node ij and also to the immediate left neighbor and to the immediate right neighbor. So, when you go back to this thing here, you have I here, ij here, I minus 1j and I plus 1j. So, these 3 points here are being used to represent dou square u by dou x square at I comma j. Similarly, dou square u by dou y square is the second term which is appearing in this, and here the variation is with respect to y here. We can again write a central difference formula like this: ui j plus 1 minus 2 uij plus uij minus 1 by delta y square, and this will be invoking ij minus 1 and ij plus 1. So, the immediate bottom neighbor and immediate top neighbor. So, when you now substitute both these approximations in this and then put this f here as f ij, I comma j here, then you have an overall expression which is like this. So, this is equation 17 is a discretized form of equation 16 at node ij, and in this equation here you have u I comma j, u I plus 1 comma j, u I minus 1 comma j, u I j plus 1, u I j minus 1 are appearing, and together. So, that means that the discretization of the governing equation at node ij here results in an algebraic equation involving the left neighbor, the right neighbor, the bottom neighbor and the top neighbor, and itself giving rise to a computational molecule like this. Okay. So, this actually encloses all the points that are being involved in the algebraic equation for this particular node I. Okay. And this presents us the difficulty that we cannot evaluate this until we know all the neighboring points, and we never know the neighboring points independently. So, that is why we write down these equations for all the points and then we solve them simultaneously. Okay. So, this is the computational molecule for this Poisson equation here, and we notice that the computational molecule depends only on the derivatives. So, the value of this fij is given by a function, it is an algebraic function, maybe constant, whatever it is not bringing u into picture. If f is a function of u, then there may be a part here, and we will come to that in more advanced other parts of this particular course. Okay. So, now this is a computational molecule. This has to be applied at every grid point, at this point, this point, this point, this point and all the points, and how many points where it has to be applied depends on the boundary conditions that we have. Okay. So, now this is our rectangular domain, this stretches up to a width of w and a length of L here. If you take this particular boundary here AB, then you can have 3 different types of boundary conditions which we had already alluded to in our earlier classes. Dirichlet boundary condition is a boundary condition where the value of the variable is specified on the boundary. Now, here this boundary point corresponds to j equal to 1. So, u of xi, so that is at for all these nodes which are on the boundary here, I is changing, but j is equal to 1. So, xi y1 and the corresponding function here g xi y1, we substitute the value of xi and y1 and you get g here, and that determines the value of the node on the boundary in a Dirichlet boundary condition. We can also have a normal gradient specified thing. So, now for this boundary here, this bottom boundary, normal gradient is dou u by dou y. So, you can say dou u by dou y at I comma 1 at this point, this point, this point is specified, and that is given by some C1 which may be a function of I for whatever it is, and this is applicable for all I for j equal to 1. So, this is a normal gradient specified boundary condition. So, this can also be a boundary condition. Now, in this case the values of u at the boundary points are known, but in this case we do not know the value of u. Now, you can also have, for example, in case of heat transfer you can have what is known as a convective boundary condition. So, you can say that the heat flux at the wall is given as minus k dou u by dou y. It is usually dou t by dou y, but here our variable is u. So, you can say minus k dou u by dou y, and it is given by a convective heat transfer coefficient and the difference between the bulk value, the value at infinity, minus the value at the wall. So, the value at the wall is ui1 at this point. At this point this will be ui minus 1 1. So, this is the value at the wall, and this is the value at infinity or the bulk value, and this is the heat transfer coefficient. So, in this kind of boundary condition the heat transfer coefficient is given and the value of the variable at infinity is a given thing, but we do not know the value of this. So, in the case of Dirichlet boundary condition the value at the boundaries are known, and it is only at the interior points we have to get the values. In the case of normal gradient specified or convective boundary condition or maybe even radiative boundary condition and all that, the values at the boundaries also need to be evaluated. So, in this particular case, for this equation with Dirichlet boundary conditions we need to evaluate only at the interior points. So, only for I equal to 1 values are known and j equal to 1 values are known, and similarly I equal to ni, which is the topmost which is the rightmost value, and topmost value is known. So, only for in between the values we need to find out. So, you have n minus 1 times nj minus 1, ni minus 1 times nj minus 1 number of algebraic equations are to be solved in order to get the value of u at all the interior points. So, this we have already done in our very first week of lectures, and so we are quite familiar with this. Now, if you want to do the normal gradient specified thing, for example, dou u by dou y equal to C1 for all I at j equal to nj or j equal to 1. In this particular case the value of u at I nj is not known, and this needs to these values, that is all the I values on this j equal to nj need to be determined. So, we can write an approximation of du by dy at I nj as ui nj minus 1 minus ui nj by delta y equal to C1. Now, this is a first order accurate approximation for dou u by dou y at I nj. Okay. So, this is because it is a derivative with respect to y, nj minus 1 and nj is changing, but the I index is not changing, and we can see that this is nj minus 1 and nj. So, there should be a minus sign here, there should be a minus sign here, and so this is a backward differencing scheme. Okay. So, this is a backward differencing approximation, first order accurate because it is involving only two immediate neighbors, and that is one possibility. So, since the value of this dou u by dou y is given here, you can now write this equal to C1, and therefore, from this you can write an algebraic equation ui nj minus ui nj minus 1 equal to C1 times delta y. So, here I have corrected the minus sign. So, this is an algebraic equation for this node u I nj. Okay. So, in the case of boundary point where the boundary value is not known, we do not use the governing equation, we do not use the Poisson equation, but we make use of the boundary condition in order to get an algebraic equation for this. Now, we can, instead of using a first order accurate thing, we can also make use of a second order accurate one sided differencing formula here, and because we are looking at nj, which is the topmost boundary, we do backward differencing involving nj, nj minus 1 and nj minus 2, and we can easily derive the coefficients a, b, c for this using the method that we have already written, in which case we write this dou u by dou y at I nj as a ui nj minus 2 plus b ui nj minus 1 plus c ui nj divided by delta y equal to the same first derivative which is given here, and this will give us a different algebraic equation for the same point ui nj here. So, here we have 1 and minus 1, and here you have a b c like that. So, you have a different discretized equation for this particular point here, this particular node here, and this again is obtained from the boundary condition here. Okay. So, now when you have a convective boundary condition, for example q wall equal to h times u infinity minus u wall with h and u infinity given, we know that the heat flux from the convective side, from external side, must equal the heat flux from the interior, which is minus k dou u by dou y, and dou u by dou y. So, this is effectively condition is minus k dou u by dou y equal to h times u infinity minus u wall, and so we can write this as h times u infinity minus u I n j equal to minus k times dou u by dou y at n j. If we make use of this second order expression, you have this expression like this. Now, we can rearrange this in terms of known quantities. So, we can bring in u I n j times minus h here, and you have this thing. So, we can rearrange this to get an algebraic equation involving u I n j, u I n j minus 1, u I n j minus 2, and in this we have a b c, k, delta y, and also h will come into picture. Okay. So, this gives us a different algebraic equation again for the boundary point. So, in this way we make use of, we incorporate the boundary conditions into our set of equations that need to be solved. If it is a Dirichlet boundary condition, then the values, known values incorporated when we derive. For example, if this is the boundary point, so in a Dirichlet condition this value is known. So, this is fed into the equation for this. In the case of Neumann boundary condition, normal gradient specified or convective boundary condition, we are directly evaluating the value of the variable at these boundary nodes by writing an algebraic equation derived from the boundary condition, not from the partial differential equation. So, in this particular case we have ni minus 1 times nj algebraic equations to be solved for uij if you have one normal gradient boundary condition specified here. So, if you, so in that way we can bring in any kind of boundary conditions into the governing equations, and we, with this boundary condition for interior point is given, is converted into an algebraic equation using this, and at the boundaries depending on the Dirichlet boundary condition or the Neumann boundary condition or convective boundary condition, we can make use of either this equation or this equation or this equation to find the boundary equations. So, together these constitute a set of algebraic equations which can be put in the form of Ax equal to b, and then we can use a variety of methods for solving this. So, in this particular way, in this example way, we can claim that we know how to discretize a given partial differential equation using finite difference approximations. So, having understood this, we will go into another feature of this finite difference approximations, which is specific for time dependent problems. So, we will in the next lecture we will look at the how to bring in time differencing, time derivatives, and what special difficulties or features that are brought in because of time derivatives as opposed to space derivatives. And with that we will be able to look at all derivatives that appear in the governing equations. That is, we have time derivatives like dou u by dou t, and we have first order derivatives like u dou u by dou x plus v dou u by dou y, those type of things. We know how to derive finite difference approximations for the first derivatives, and we also have derived finite difference approximations for second derivatives like mu dou square u by dou x square, dou square u by dou a square and all that. So, we will be armed with a set of designer finite difference formulas that we can design as per our demand or as the problem demands in terms of one sided or central or this accuracy or first order accuracy, second order accuracy, and we can convert any given partial differential equation into an algebraic equation at a given node, and we do that for all the nodes and then convert into Ax equal to b form. So, in the next lecture we will look at what to do for finite difference for derivatives involving time derivatives.